Thermodynamics. So the ASME last night we had talking about stuff that's happening today or tonight and coming up. If you weren't at ASME, tonight's the free taco bar from the mechanical construction. It's actually mechanical contractor, which mechanical contractor is heating, ventilating, air conditioning, which is, the heating, ventilating, air conditioning, fire systems, all that. It's piping and it's mechanical and it's pumps and stuff. They are hiring from here. They like us as Central, what we do here at Central. So that's basically a recruitment event, once a year kind of thing. And then there's another one coming up. This is more about, less about mechanical contracting and more about construction in general, but there are a couple companies coming in November. There's things up on the wall, but the main thing is this thing tonight. We've had 10% of the class last year got hired through the mechanical construction, and there's an MCA club that is sponsoring this. They get a lot of support from industry. So just to make sure you're aware of that, 5 o'clock tonight in the big room downstairs, and they're having a whole bunch of mechanical guys there with a bunch of stuff from the Taco Del Mar. I think they bring in, not just pizzas. And let's see. Also like to bring up Ryan in the front here was mentioned to me that the whole clicking thing, he's got a sensitivity to that, so try and keep that stuff down. It gives him migraines, which really sucks. Just to be aware of that. Tapping and clicking and that sort of things. Let's get to this, what we were working on yesterday. We're given a couple things here. We figured out it was a colder temperature than the saturation temperature that goes with this pressure. Therefore, it's been subcooled, or you could say it's at a higher pressure than saturation pressure for this. It's a higher pressure. You could call it compressed. Either way, it's not saturated. It's a liquid. On this one, we figured out at 30 degrees C, there was, and we were told it has this much specific volume. That value was, if you looked at the saturation for, basically what you do is you look at the saturation table and say, is it in saturation or not? And then if it's not, then you say, is it below or is it above? And in this case, we found this value was between the value if it was all vapor, saturated vapor, and the value if it was all liquid, which means it has some liquid and some of the liquid is turned to vapor. And when we knew that, so yes, it's in saturation, then we go back and say, therefore, at this temperature, it must be the pressure that's the saturation pressure. And then what we then knew is the saturated mixture. What we didn't finish doing was how mixed is the mixture. So here's the value that they gave us, how much that liquid and vapor together, how much space they're taking up. It went from this liquid value up to that value. That's how much it's expanded. This is the actual value. This is the liquid value. Over the range that it could have gone was from the liquid value to the vapor value with 100% vapor. And I didn't crank the numbers on this last time, but if you do crank the number, it comes up with, it's going to be less than 1 because this is less than that value, so this number is always going to be smaller than that number. It's between 0 and 1. and we got it 0.8207, which works out to, you know, got that 82% of the mass is vapor, and you know the rest of it's still liquid in the bottom. Volume-wise, it's going to be a whole lot bigger than that because the vapor by mass is like 1,000 times bigger. So it might feel like there's almost nothing in the bottom, and we'll see that tomorrow in lab. We're going to do an experiment where we actually take some refrigerant, and we're going to let some out, do an energy balance on it, but we'll do the numbers and you know what the specific volume number is in the can, and it's going to feel like there's nothing in there, and it might be like 75% liquid by mass, but the volume, you know, it's not about volume, it's about mass, and the vapor's, you know, 1,000 times bigger. So, and then we looked at this one. What we knew was it is saturated vapor. It is at 320 kilopascals. And if you know it's saturated, then you know what the temperature is, because the only way it can be saturated at this pressure is to be at that temperature. And if that's the case, to give us data for this. And the last one, I bet you, it's going to take us into the superheat tables. Yep, it does. So, and that is, we're metric.
Superheat is a refrigerant, right?
Yep. Okay, so temperature. So how do we know we're in superheat tables? I'm just guessing. But I look in the saturation table.
Saturated refrigerant?
Oh, let's see, refrigerant. I'm on steam. They do water first, and then they do the refrigerant. And the only refrigerant they've got tables for is R134A.
Because
there are a bunch of them, but that is the predominant one.
If I go to IO994, is that what?
What now? What, 994 maybe? Yeah.
So if you go to 600 and it's the temperature says 2155, but we have 600 here, that's how we know?
100 degrees C, well,
What's 100?
So 100 degrees C and 600. So the question is, what we know is we got 100 degrees C and 600 kilopascals. At 600 kilopascals, the saturation temperature is 21 degrees C. So room temperature, that says that the 600 kilopascals is the absolute pressure inside of our like refrigeration thing. The temperature is higher than that. So that means it went to vapor and then we heated it some more so that it's outside of this bound. So now we know we're looking at a superheat table. So I'm going to go to the pressure, and the superheat tables, because it goes up a long ways in pressure, 600 kilopascals becomes 0.6 megapascals. And now if we look at 100 degrees C, that tells me all of these properties are all true when you're at 600 kilopascals, which would be 6.6 mega, and 100 degrees C, this line is correct. If we went to 700 kilopascals, 0.7 mega, then that would be true for this line, or a different temperature would be here, or whatever. You notice there's a gap in some of these tables, and that's because here's the saturation value, and now at 20 degrees C, what do you get? Well, the problem is it's not superheated at 20 degrees C, so that line isn't there because that would still be in the saturation zone. But at 30 degrees C, you've got some data for it in the superheat. So, long story short, we need volume and phase. What we know is superheat is the phase.
So you just do superheated?
Yeah, just plain old superheat. Don't have to do other things. And then if I look at the numbers, my
The
specific volume,
0.4
yeah, 0.04
7900.
479. Oh, 2 hours. And that's. Do you see where we're getting all that stuff? That's really important to. And when in the homework, don't blow off this thing because you'll be doing a lot of this. And if you're not comfortable with doing this, it's going to be a lot of discomfort down the road. You'll be just slower in everything. So this is just an exercise, but you'll be using these when we're doing refrigeration and steam. So we ended up with a table that looks kind of like this. Filled it in. They only gave us 4 categories, but the enthalpy, the entropy, all those other properties, they also would be, once we know 2 of these things, then we can fill in all the rest of the properties are going to be true. So, that was so much fun that I think we ought to do another one. Oh, looky. There's one right there. Let's do it for water now. I've got a nice round, this first one, I've got a nice round number for temperature, so I'm going to use the temperature table. So that's table A11 on page something. Looks like 993.
What? We don't want to copy that.
Oh, wait a minute, that's 134. That's a refrigerant. Oops. 1, 2. There we go. Temperature table for saturated water. Watch. I will find people on the test that will do something about steam and they'll get the data for refrigeration. Make sure that this matters, water or refrigerant, right? It's different properties. So now we've got, what was our date? We're looking for 150 degrees C.
Okay.
Yep. 150 degrees C.
Anything else?
And it said we had a specific volume of 0.39248.
So it's a saturated vapor?
150. So 39248 is there, and this is liquid, that's vapor, so it says we are in saturation, we have 100% saturated vapor.
Do we use that pressure then? So do we use 47616?
Yes.
Okay.
Because the only way it can have that volume is if it has the pressure, saturation pressure.
So you need at least 2 out of the 4, right?
You'll be given 2, and if there's more than 4, we only have 4 here,
Right.
but whatever, when you
at
have
least
2
Okay.
2 characteristics, that 2 properties will only occur at one state with temperature, pressure, everything else. So, what's that look like? So there we have that. Knowing those 2 things, we found out it was this. Because that's the case, then we know we're at the top end of saturation, but we're still there. Next one, we're going to 250 degrees C and 1,000 kilopascals. So, at 250 C, 1,000 kilopascals. Here's 250, 1,000 kilopascals. What does that mean? Yeah, if it was what this says is you need to have at this temperature almost 4,000 kilopascals to keep it to keep at that temperature, to keep it in the saturated, to keep it at its boiling point. We've released it. If there's another temperature, let's look at another one. What if we had the 1,000 kilopascals at, it says 1,000 kilopascals, it would be boiling at 180. But we're at 250, so it's expanded, whatever. We're superheated because we're hotter than that for the pressure involved. Or we have less pressure for the temperature involved. But that's, I think, Mark, you look at the pressure and see what the temperature is, and if you're above that temperature, then you're superheated.
So we have 1 megapascal at this point?
Yes. So we got 1 megapascal, 250 C. We need to find the specific volume.
0.23275.
So let me get this cranked up. So we're at 250 and 23275 is, and the only way,
And then we'll just call superheat.
and it's just superheat, yeah. If you're in saturation, then you're either all liquid, all vapor, or more likely you're somewhere in between. And then it gets complicated. How far in between are you? So that's how I use those superheat tables. Let's get back to this one. We've got 50 kilopascals, and it tells me we're a saturated liquid.
Okay. So we need to find volume. Okay, got it.
I want to find
0.001.
saturated liquid at 50 kilopascal.
Temperature.
We know that. We know that. The temperature will be because it's saturated. Just out of curiosity, is 50 kilopascals, is the temperature going to be really hot or really cold? It's boiling now.
Colder.
Yeah, it's going to be colder, definitely colder than 100 degrees C, which is what we at 100 kilopascals. So it would be 100 degrees C. So 50 kilopascals, and it's saturated liquid. It's 50. Boiling temperature it is still pretty hot, 81.32 degrees. And specific volume is, you can read straight off because it says it's liquid, and it's 001030. It's expanded a little bit from the ice water, which would be just 001, 3% bigger. The next one we have, I'll just read this one off. It's at 100 degrees C, and we have a specific volume of 1.00. So 100 degrees C, and specific volume 1.00. Uh-oh. 1.00. Are we between these two values? It's less than 1, it's more than 0.001. So that says, yay, we're in saturation. We know where we are. Where in saturation are we?
Can you go over that again? Sorry. So I found the 100 line.
Yeah.
Okay.
100. And then up. We're on the pressure table. Yeah, and I want degree. Thank you very much. I was just doing that to see if you were were awake following this. Yeah, that's it. As it turns out, because the temperature is about the same, we're going to have about the same result just out of luck. because at 100 kilopascals, we're at 100 degrees C thereabouts. So now we're at the right temperature, thank you very much. 1.67, we're between those two numbers. So the question is how far between them are, how much of the mass has expanded. So,
So when you say between the two numbers, you mean the saturated for vapor and saturated for liquid?
it's saturation mixture. We're between being all saturated vapor and all saturated liquid.
Okay.
Some of the liquid turned into vapor, but it's still boiling.
Okay.
So it means the temperature, we now know the temperatures, or the pressures, 101.42. That's the only way you can be in saturation at the temperature of 100. So our pressure is 101.42. And we know we have a saturated mixture, but what we don't know,
Is it percentage?
yeah,
The thing you did last time.
so we have to do an interpolation, get between the 2 points. The polation is the point, and inter is between the points of these 2 points. The spread between these two is that much. That would be that it all expanded, but we only went up to 1 instead of 1.6. So 0.0010. See what we got. 1043. No. 0.6720. So here's what it looks like. Basically, it has expanded from all the mass here up to that much. How much could it have gone? All the way from here up to that much. So some of it didn't get converted. How much of it did get converted into vapor? And this proportion will tell us the mass amount that's in vapor space in the box. So, I don't know what that comes out as. 999 divided by 1671, basically. 60-some% of it. 6978. 6978? 59? I'll just give it 3 digits there and call it. So 59.8% of the mass is vapor. It's taking a lot more space than that because the vapor expands a whole freaking lot.
Now, why is the 0.59 vapor not liquid? It's how the other way around.
By the definition of the quality, this term here is defined as the mass percent of vapor.
Oh, okay.
Because if it was all liquid, this up here would go to 0, and if it all turned to vapor, this number would be the same as that number. It goes to 1, and they just do it in terms of how much has it expanded, and the expansion is from the vapor.
Vapor, huh?
So it's the mass percent of vapor. Okay. So that was fun. All right. You have a couple of these in your homework. Many of you will have trouble trying to make sense out of, how do I know it's this, how do I know it's that, and you'll struggle with it a bit probably, but eventually it comes around. And if you have questions, does anyone have specific questions or non-specific ones about any of that at this point?
So a test-worthy question?
Say again?
So a test-worthy question?
Yes.
I do on the lab.
Okay.
I was struggling with calculating the density of the pressure. I couldn't get my units to work out right.
Density, I mean,
The density of the unknown fluid.
oh, okay. So, the question was in the pressure lab, pressure equals rho GH. Have any, we had like some pressure at with some height involved, right?
Yeah.
Um,
And then we were trying to calculate the density. And I got numbers that look good, but I couldn't get my units to work out right.
and you know what, it probably is force versus mass kind of things. So, density is pressure over GH. And I'll make something up here. It'll be the same kind of conversions. Let's say it's, let's round numbers, 100 kilopascals and 9.81 meters per second squared. And the height is,
0.24 meters.
oh, but,
Or 0.25.
okay, I better not do 100 kilopascals. What kind of pressure you want? Because that's going to end up being like air density or something.
Oh.
Because 100 kilopascals with water would give us like 30 meters. So, I don't. Does someone have a pressure or actual data you want to?
11.3 kilopascals.
Okay. And what's our height?
1.11 meters.
So, kilopascals, we've got 1,000 newtons per meter squared is 1 kilopascal. And 1 newton is 1 kilogram meter per second squared. So kilopascals cancel, per second squareds cancel. Oh, there we go. What else? Newtons are going to cancel. And let's reorganize ourselves here. We got a meter times a meter. Meter times a meter.
Meter square, you can cancel.
And a meter's, well, this is on the bottom.
Ooh.
And these are on the bottom.
So it's
that's
going to be
meters
meter
to the
fourth?
fourth.
Meter
I'm
fourth,
going to cancel this, use this one to cancel one downstairs there.
meter third.
And somewhere here we had a, where did the kilogram go? Oh, we
It's
don't,
up top.
that's what we want, yeah. So I end up with 11.3 divided by 9.81 divided by 1.1 times 1,000. And we end up with meter and meter, so we got kilograms per meter cubed. That sounds like density.
Yeah.
And I don't know what the number is. Right?
I just want to ask, I did a different conversion factor where I just said 1 kilopascal is equal to 1,000 kilograms over meters times seconds squared, because I found that in the book and that works fine as well.
Yeah.
Okay.
That's just, yeah, that's
Just
just
a
bundles,
passcal.
that's just bundles a couple of them. So, yeah, what does that give us?
It's right around 1,000 something. 1,000 something like that.
Yeah, because it's 11 divided by 9.81. Something like that, 1,100, I don't know. Yeah. So that's,
Like I said, my numbers were looking good. I just couldn't get back.
yeah. So that's, the trick is unbundling the bundle, you know, a kilopascal is 1,000, and then it's newton per meter squared, and then what's a newton? And take it down to the basic units, and it'll usually wash through. Well, that was so much fun. What else, how do we follow that up? That's a hard act to follow. And this is where I like to say, we don't cause problems, we solve problems. So here's another one. Okay, we did all these tables, and that's nice to find the properties. Now here's how you might be using it. I've got a saturated water vapor mixture. Uh-oh. It's saturated, that's good. I know where their table is. And it's water and vapor, but how much? At 90 degrees C. Total mass is 10 kilograms. The vapor mass is 2 kilograms. What does that tell me about my quality?
The vapor takes up 1/5.
No, it doesn't
That's
take up
1/5 the mass.
1/5 the mass, but that 1/5 mass expanded 1,000 times. So what it tells me is my X, that value, the quality, is 2 out of 10, so it's 20%. 20% of the liquid has turned into vapor at 90 degrees C. And really what happened, you had a tank of some size, I don't know what size it is, but whatever size it is, at that temperature, that's the only, at that volume, if it's under, there can only be one pressure at saturation. If it's at that pressure, that volume, all these things are interrelated. So I need to figure out what my specific volume is for this. So got a saturated mixture. Total mass of 10 kilograms. Mass of vapor is 2 kilograms. All right, that tells me I know my quality.
Do you want to change to what you're doing?
Yeah, I'm just, I'm going to look up some properties here. Well, I'll show you what I'm writing here. That's how we're setting it up. Got a box. It's got 10 kilograms in it, 20% of the mass, but not of the volume. "10 kilograms of water, 2 kilogram vapor." So, because there's both water and liquid together, the only way that can happen at that temperature is if it's in the saturation zone and the saturation. So pressure at saturation at 90 degrees C, and it's water, it makes a difference what it is. Different result if it wasn't water. So 90 degrees C, yeah, temperature table. 90 degrees C, it can only happen at 70 kilopascals. If you open the valve for that tank, is it going to shoot stuff out or suck stuff in? Suck stuff in. This is all absolute pressure. So atmospheric pressure is 100. We open the valve, it's going to be a vacuum. So I now know my pressure is 70.183 kilopascals. That's question number 1. Question number 2, how big is the tank? Well, I know that if it was all liquid, we'd have a volume of 001 of 2.1036 meters cubed per kilogram. If it was all vapor,
2.3593.
got 2.35. What was it? 93. Got 93 meters cubed per kilogram. And now I'm going to do this two different ways. I've got that data now. Everyone see where I'm getting the data? When I found what the temperature was, it's in saturation. The first column's volume of liquid per kilogram, and this one's volume of vapor per kilogram. Now I'm going to use that data. And what do I know? I could say volume total equals volume liquid plus volume vapor. I've got, it was 10 total, took away 2 of it vaporized, so I got 8 left. So I got 8 kilograms liquid times 0.001036 meters cubed per kilogram, plus I've got 2 kilograms of vapor times 2.3593 meters cubed per kilogram. And I want each one of those terms separately, so someone have happy fingers there. We want 8 times 0.001036.
In the end, I got 4.73.
Okay, and in between, so that's good, but I also want to look at these separate ones.
For them both, for the first one, I got 0.008288, and the other one, that I got 4.7186 for the other one.
So where is most of the volume? 20% of the mass is, 99.99, I don't know, some huge proportion of the volume. And 80% of the mass is in a small volume. So the mass is what carries the energy. So we don't really care about the volume so much as the mass. So let's calculate this one other way, which is, so this way we said how much volume in the liquid and how much volume in the vapor. And we figured out the total volume. Now let's do it sort of how you'll be doing it more likely. Let's see. Volume total is going to equal mass total times specific volume of the fluid plus X times Vg minus Vf equals 10 kilograms times 0.001036 plus 0.20 times 2.3593 minus 0.001036. So I'm using the properties now. I want to find the specific volume of the mixture. This is sort of what we were just doing when we were doing the sort of the quality thing back. Volume of the fluid plus 20% of it expanded this much from the fluid to the gas. 20% expanded that much, add it to this value. I want this value, and then we'll multiply by 10. So 0.2 times this minus this times 0.2 plus that guy.
0.4726888.
And I'm going to use my lightning quick supercomputer brain to come up with the new answer is rounded up to 4.73 cubic meters. And it's a check on our other system. But this was saying, we could determine this property. And these are like way too many digits for, the tables come with 5 digits, and most of the experimental stuff is 2 or 3 digits when we're doing it. But this was the actual properties for that saturated mixture.
What's the first one? Says the volume of, what's that?
Total volume.
Total volume equal to
Total mass times the specific volume per unit mass of the properties.
Okay.
You'll be using these formulas more. The whole point, this one's more intuitive in that this much was liquid, this much was vapor. This is basically, we got 8 kilograms, it's going to be about 8 liters. And this is going to be like almost, 4.5 of those tanks in the back of the room. But those tanks are holding the vapor. So this quality thing, frankly, clouds, when you see a cloud in the air, what you see why you can't see through it is vapor droplets. Steam itself, saturated steam or superheated steam, is clear like air is. It's just transparent. But if it starts to condense, you get these tiny droplets. And if you get someplace really foggy, they're like dropping onto you. You get wet. But even a cloud, I don't know what the quality in a cloud is, but I bet you if you took all the air out of it, the vapor versus whatever, I bet you it's a pretty high, of the water vapor that's there, it's probably pretty high value, like 90% or something, or more, maybe 100. Or, 0. A lot of it's liquid. What you see that's white is liquid, so it's mostly liquid. They just haven't congealed into lava.
So it would be a low percentage of vapor, right?
Low percentage of vapor in a cloud. The problem with clouds is it's a high percentage of air. It's not just about water. And then you're talking about 2 different substances, and this whole thing is not really relevant. So I think that's probably enough torture for today, but we'll do it again tomorrow.
Killed 8